Let us now go to the second laboratory work of the adaptive control in mechatronics and robotics. Now we need to work with second order plant. Here we can see in tutorial some theory that we need to read. Here we can see our model for MATLAB. So as you can see, we have the second order plant. We have two integers in the feedback of error. So we have plant, reference model, and adaptive regulator. Please pay attention that now we have gamma A and gamma B for both of our state space variables A1 and A2. So we have gamma A1 and gamma A2. Gamma B is only one gain as it was. So we have the same tasks for all the laboratory work. For the first part, we need to design the stable plant and investigate it. Then we need to compare the stable plant with reference model. Then we need to design adaptive regulator. Then we need to vary parameters of adaptive regulator GA1, GA2 and GB. Then we need to calculate KA and KB and check if KA and KB calculated, they are equals to KA steady from the model. And then we need to work with unstable plant. We need to do the same steps. So we need to investigate unstable plant, we need to compare it with reference model, we need to design adaptive regulator for an unstable plant. Then we need to vary parameters of the adaptive regulator for an unstable plant and calculate KA and KB. Let's take some variant, for example, variant number maybe 3. So we have the stable plant parameters and unstable plant parameters. Let's go to MATLAB and simulate something. Now we need to define A2, A1 and B. Let's send data to workspace. Obviously, the plant is stable. Now let's look at reference model. We need to define variables AM1, AM2 and BM. Now we can compare our plant, the blue plot, and our reference model, the red one. So we can see that they are different. Let's design adaptive regulator for the purpose to make our plant graph looks like our reference model plot. Now we need to define minus GA1, minus GA2, and minus GB, as well as P. As you can see, data 1 plot is much closer to the reference model plot. Please don't forget to clear the tick interpret vector parameters as one-dimensional for the constant 0bm. We don't need the string, we need a column. So we need to clear the tick interpret vector parameter as one-dimensional and press OK. All the same blocks are without any changes. So now we want to check if something will change, if we will change gamma A1, gamma A2, and gamma B, while P is constant. So let's do it. Let's do it again. Hold on, read on. Here's our reference model, and here's our plant. The first one, the blue one, is for GA1, GA2, and GB, they equal 1. And the second one, for GA1, GA2, and GB equals 0.1. So we can say that if we are reducing gammas, so the step response looks poor. Let's increase gammas. Look, we have magenta plot, so the plot of our plant looks like a reference model. So, conclusion, increasing gamma makes step response of our plant look closer to the reference model. Now we need to calculate Ka and Kb and compare them to the ones we get from the simulated system. As you remember, we need to change step as input to pulse generator. Pulse generator should have pulse width 50%. Period of time, well, we don't know yet, but let's choose displays and show Ka and Kb. Please don't forget that Ka will be a matrix. So you can see Ka equals minus 4.8 and minus 0.9, and Kb equals 4.5. Let's look at the step responses. Well, step responses looks fine. Let's calculate Ka and Kb. So Ka calculated equals minus 1 and minus 4.5. Let's calculate Kb. Kb equals 4. Kb equals 4.5. Ka equals minus 1 and minus 4.5. Let's increase gammas. Well, for the pulse generator period 10 seconds, and for gamma A1 equals gamma A2 equals gamma B equals 10, we have Ka calculated -1 minus 4.5, Ka simulated -1.002 minus 4.541. I think it's quite close. And Kb calculated equals 4, and Kb simulated equals 4.072. I think it's quite close as well. Well, let's change the parameters and check the unstable plant. So here is our unstable plant. The response of our unstable plant is quite okay, but maybe we should increase gammas. Well, let's check Ka calculated and Kb calculated for the unstable plant. Ka calculated for the unstable plant equals -5 and -5.5. Let's calculate Kb. Kb equals 4. So we have Kb equals, in simulated version, Kb equals 4.8 and 38, and Ka equals -6.364 and -5.307. Well, if the period of time of pulse generator equals 9 and gamma A1 equals gamma A2 equals gamma B equals 20, we have Ka equals -5.495 and -5.006. Actually, it's quite close to what we have calculated. And Kb equals 4.013. And calculated Kb equals 4. Actually, it's quite close as well. And the plant, unstable plant simulation gives us this thing. So we have a shelf on the top. Maybe let's compare them with reference model. Actually, as you can see, our plant and our reference model, they are very close to each other. So the blue plot is our plant and the red plot is our reference model. So as you can see, they are very close to each other. That's good. Actually, it was laboratory work number 2. Thank you for attention.